Wilson.
And today we're going to be explaining our 375 project. Okay, so for starters, I want to jump into the intro.
Kevin?
Wow.
Dude, is this like your third monster? Is this like your third monster?
No, it's my fourth.
What? Oh, okay. But isn't it like a lot of caffeine in your body?
I don't know. I have no idea how to track it, so I just keep drinking.
Sounds like a problem.
It might be.
But what if there was a way to track it? Over the past few months, Team Sensor has been working diligently to develop a device that can track the growth and decay of consumed caffeine in a person's body. To achieve this, Team Sensor has been using spectroscopy and infrared detection. Of course, there was a lot of trial and error, and there is still a lot of research to be done. However, in this video, we will break down Team Sensor's results and explain our goals heading into the future. Thank you. Before Team Sensor could even begin working on their project, Kevin had already developed math formulas from a previous semester that can track the growth and decay rate of caffeine. This gave Team Sensor a step in the right direction. Kevin explains his process and reasonings on why he changed his formula from a piecewise function into a differential equation.
Like the three of us together that was trying to figure out different mathematical equations to where it was like piecewise, difference, and differential. Like we started with difference equations so we can take it on every interval of a step, but then we broke it into steps and changed it to a piecewise equation. And that piecewise equation was taking different pieces like sips. It's like you decay it at this sip, and you take what you decayed and put it into your next equation, and you decay it again, and you keep going however many steps you did, and we did it in 12 steps. But then we changed it into the differential equation, which takes it at every single step, given your input of caffeine, given the time that you had it in the original dosages, and it'll decay it at every single step at one time. It's a continuous decay. Instead of decaying it in like say 12 or 4 steps, it will decay it for the entire length of you having it inside of your system.
So spectroscopy is the study of the absorption and emission of light. It involves splitting the light into many different wavelengths, also known as a spectrum. Here, Kevin gives examples of how finding the inverse of this transmittance will give you the absorption of that wavelength. Absorption will tell you if the chemical is inside of you and how much of it is inside of you at one time. Kevin also briefly explains how we will use this concept to detect and track caffeine in our project.
Depending on how it comes in, needs to be like, say, if this is 5 mgs, this is say 10 mgs, and say this is 50. Well, that's good because you can trace it back to a point, and this is kind of what the results that we're trying to get. But even if we don't get the results, and let's say it behaves completely differently per each milligrams, what we can do is we can like half step it. So like say we can take some big dosages, which we did already. Like you'd say per milliliter to per milligram is like starts at like 0.88 of a dosage, and we just half step it down to like 0.0. I think it's 275. So it's like you half step it down, and depending on what dosages you get, even if it behaves at like different points, what we can do with the power of mathematical modeling is we can just make an equation that can hit every single one of these points. So even if I can't get this constant of a desirable peak which just says, hey, this is linear, it comes back to one section, what we can do instead is even if it misbehaves horribly, and the peaks of each half step milligram is all over the place, we can just make some equation, whether it be a differential equation, whether it be maybe a second order polynomial, or some type of integrand equation. We can make something that represents these peaks, and then we can just put our data into those peaks to check to see if you have that amount in your system. Because like say,
in this project, we chose to use the Jetson Nano. We chose this device because in the future, we hope to implement machine learning into our caffeine tracker. And the Jetson Nano allows us to run multiple neural networks in parallel for multiple machine learning applications. Attached to the Jetson Nano is an infrared light and sensor. The Nano is plugged into a monitor to display our results. For starters, I want to mention that we are using Python, one of the best programming languages out there. Okay, so now we're jumping into the software portion of our presentation. So basically, our software, what it does, it takes this reading in from our infrared light and sensor, which is going to be our pin 12 and pin 21, right? And basically what it does, So every time the sensor is hit, that's going to be our fields category, right? And our rows is basically that number, right? So it's basically an array, okay? So while it's running, we're going to be actively writing and updating a CSV file. So while it's true, while it's running, every time the sensor detects it, it's going to update our count variable by 1, okay? And then once it does that, it's going to pin that variable back into our array, right? So as it does that, it's actively writing into the CSV file and updating it. So when it's not detecting it, it's saying no power, no power. That's what it's printing right here. But when it does read it, it's printing out the 1 and then the 1 and the 2 because it's actively updating the CSV file. And from here, we hope to use in the future to actively update data that comes from detecting our caffeine. So we'll be able to actively display the data live time of what's going on. Devin, you still drinking that Monster?
Yes, I'm still drinking the Monster. You understand? I haven't slept in 4 days. I need one. So
right now, this is when we're not detecting anything. It's saying no power, right? But when we actually detect it, right, it starts to pin each detection to our array.
Let's do 7, 6, one more.
Yeah.
All right, we'll stop there. So we'll stop detecting, kill the program, and then we'll check if we'll say ls. Well, if I can ls, and it'll show you that we have this file called infrared data, and we'll do a cat. Let's just show you the contents inside of it. And then it'll show you the contents of what came inside.
So it actively updated the CSV file.
It actively updated the CSV file.
We did it. We were able to sense light into a CSV file using an infrared sensor. Now that we accomplished that, we are now going to discuss our future goals of how we plan to take the infrared spectrum of caffeine and use that data to display the growth and decay rate. Furthermore, we will also discuss how we plan to implement machine learning into this project. We want to talk about some future goals that we want to hit in the future.
Yeah. So number one is like we have to be able to take this from a chemical testing to real testing. So right now we're just doing different caffeine testing with different liquids. Like we're going to do chloroform testing next. And we are doing right now, we are getting results from that. But we need to take that from when we're done with this, when we get a consistent peak, move into doing different testings with hopefully either different liquids that have a combination or some type of bond with caffeine to show how it bonds to different things, and eventually move into blood testing to where we can see how it behaves with blood, and hopefully find some pattern into how the IR light behaves with it, and from that pattern make some type of mathematical equation that will represent those peaks.
Right. And just talk about the caffeine itself. We need to figure out what type of caffeine we're actually detecting, right? So we need to figure out, are we detecting the caffeine that is before it's being metabolized, or is it the caffeine that's being after? Because that also has different effects within the testing as well.
Yeah, so you have to figure out like if it's, you're detecting the actual caffeine as it going into the body, which is how it's being absorbed and distributed through the body, or if you're detecting it after it's metabolized and turned into what's called metabolites, which is the different compound that the element will turn into after your liver gets done metabolizing it. So it's like, which one are you actually tracking? It's more probably going to be the caffeine before it gets to the liver because it distributed into the bloodstream already, but that's still something we need to figure out.
But once we figure it out, or if we don't figure it out, we still need to figure out the behavior of it, and we need to be able to get that scan with a infrared light.
Yeah, we need to be able to hook up the light to some type of a device that takes out visible light, like a watch or something, and be able to scan it to a person and actually detect it. And hopefully we can move into also making a user interface with it, like make some type of website and a mobile application, which there already is kind of one, but I'd like to redo it and make it more dynamic, I guess you can say, to be able to take in the data in a different way. So after we make like the math equation, we're able to hook it into a neural network and then be able to display that data through some type of mobile app.
I was just about to say, take that data and display it into some kind of model in a neural network, which we've been looking at, like recurrent neural networks.
Recurrent neural networks takes in a time series of information. So it's called a feed forward neural network, to where it's like it takes in a initial time of say T is equal to 0, and it just keeps going for as long as you want to. So it's like if you wear a watch that has the infrared light on it all day, it can just continuously take in that data sequence, putting it through some type of an activation function with certain weights, and be able to learn how fast that person can or cannot decay the caffeine. And it should be able to individualistically learn for each person that is on the website.
Supposed to.
It's
Supposed to.
It will in theory.
Bro, Kevin.
Bruh.
Kevin. This is why you need to track how much caffeine you use. Kevin.
Oh.